afternoon session, and it's my pleasure to introduce Rimanyi, who will tell us about a geometric problem in machine learning with flavor of singularity.
That's correct. That's correct. Thank you. Thank you very much for the invitation. The journey we will go through is starts with singular learning theory. And there will be some singularity theory that goes to some geometry. And then that will go to quiver algebra. I should some integer programming, and then some convex geometry. However, I should tell you that this work grew out of a lecture that many of us attended who are here in the audience. There was a lecture in the special semester last spring where Simon Lehalleur, who is my co-author on this work, gave a lecture on singular learning theory, roughly about this part. And then I really liked the topic, and then some research came out of it. And I will tell you about it. But this part that I heard there, I still don't fully understand. However, it is clear to me that many people in the audience understood it much better than I do. So when I come to this part, then I want you to take over the talk, especially Lorenzo.
You got the wrong impression.
Okay. And because of that, because I don't fully understand this part, I will actually give a very, very brief outline at the beginning, but after that I will pick up this thread here, and I will talk about the tail of this story, which I understand very well, and I will come back to the singular learning theory part. So let me start with some very the outline of what happened here. And the outline is that the part of machine learning that I read has two mottos. Motto one is that over parametrization Can you read this color? Yes. Okay. Hurts generalization. You have to get used to the vocabulary of machine learning people. So I'm going to translate to you what it means. What they call generalization is not what we call generalization. We call generalization when we generalize a theorem. What they call generalization, I would call it prediction or extrapolation. So imagine that, okay, so I'm going to give you the phenomenon in an example, and then you will understand what happened. Suppose that your task is to give a good model for this data and generalize it here. We want to find, want to predict what the value of this data if this is my input, right? And of course, if you look at it, then you see that the good model to do here is that I should model this data with a degree 2 polynomial. And if you do that, you model this with degree 2 polynomial, then you will get quite a good generalization. They call it generalization because usually where they want to apply it is very far from where the data is. Again, I would call it extrapolation. But that's what they call by generalization. By over-parameterization, they mean that I made the choice of choosing my model to be a degree 2 polynomial. If I had over-parameterized this problem, and I chose my model to be a degree 200 polynomial, then the solution would be absolutely perfect here in here. It will be a degree 200 polynomial, and possibly totally wrong generalization. So it's a very intuitive statement that it is. We all feel that over-parameterization hurts generalization. Okay, I'm going to talk much about that. And motto 2 of machine learning is that it doesn't. So ChatGPT and company are very powerful. They are highly over-parameterized models, and generalization works fantastically. So right, so that in this talk, sorry.
Which version?
Okay. So what? Okay. So today we will learn a mathematical theorem towards the end, where that can be phrased as a mathematical underlying for this model too. That I will explain that the formula is such that it's over-parameterized, but still it's not hurting generalization. But it's an empirical fact. So the good models, called neural networks, you over-parameterize them, and because they are singular, then the motto one doesn't apply, and that's what we will quantify today. Should I talk about neural networks so everybody know what neural networks are? Okay, when I come back to the story, I will talk about neural networks, but
Just use them.
okay. So what I want to jump ahead,
You don't use?
what I will talk about at the end is that for neural networks, what happens is that you train your neural networks, and if you made n steps in the training, then the error will be measured by either. There are several ways of measuring the error. One is the Bayesian generalization error. The other is the some normalized free energy, and you want them to be small. And okay, I remember this better. So your feeling is that the D is the number of parameters in this over-parameterization. Then that the Bayesian generalization error should be roughly the half of the number of parameters over 2 plus lower order terms. Okay, I will not talk about the other one for now. I will come back to that later.
So what is Bn?
Bn is the Bayesian generalization error. Somehow that's something that I will measure towards the end of the talk, and that it measures that when you want to train your network, then after n training steps, how far you are from your optimal what you want. Oh wait, I'm sorry, this will make sense. This is n. I'm sorry. Now it makes more sense, okay? Okay. But what the singular learning theory does is that this replaces this d over 2 with a number, some kind of low canonical threshold, real low canonical threshold information, which is d over 2 if your model is regular. But neural networks are not regular. And that's the point, that we will calculate that this number is much smaller than d over 2. And that is the motto 2. And even when you
But
take,
it's good for us. It would mean they should use singular models.
yeah, and that motto 2 very often phrased in a different way. It is phrased in such a way that neural networks are singular and is good. This is probably actually a title of a paper. Correct. But then in this machine learning literature, the story is mostly empirical. So the paper that we started to look at the beginning, or maybe Simon started to make it bigger, it's written in the language of mathematics, that there are theorems and proofs, but it's very empirical. So very often the proofs are that we done lots of experiments, and then here's the graph, and then you see that it goes to this and that. So we will do some mathematical statement that recovers actually the corrected versions of those statements. All right. So this is my outline of what will come to the end. But now I will just forget about the motivation, and I will phrase the geometric problem and just do proper mathematics. And then we'll come back and I will tell you about singular learning theory if we have time. All right. So this second entrance, where we can go into the story, comes from undergraduate mathematics. You teach undergraduate linear algebra, and then your students will realize sooner or later that matrices can multiply to 0. So for example, if you consider, now let's start with 1 by 1 matrices. And I want to understand when their product is 0. And actually, it's not your undergraduate students, but your kindergarteners. They will know that I know why this has happened. Either x is 0 or y is 0, and these are components. Actually, these are the two components of this variety. And now, what happens if you want to multiply 2 by 2 matrices? So how can a product of 2 by 2 matrices be 0? And then now your undergraduate students will realize that either x is 0 or y is 0, or the rank of both of them is at most 1, and the image of one of them, well, what did I put? The image of y, okay, sorry. Image of y is contained in the kernel of x. And these are components again. This is what your undergraduates will realize, that there are three possible reasons for 2 by 2 matrices to multiply to 0. Of course, component is an algebraic geometry concept, so that your students will not know, but none of them is contained in the others. These are 3 components. This has codimension 4, this has codimension 4, and this has codimension 3. Let me give a few examples, if you don't mind. Now, I am going to ask the same question for 2, 3, 2. Okay, what do I mean by this? Instead of writing all of these long things, is that I'm multiplying a matrix 3 by 2 with a matrix 2 by 3. So what I drew here is the linear transformation. One of the linear transformation goes from 2 dimension to 3, and the next one is from 3 to 2. And I want to, I'm talking about the variety that the product is 0. And the claim is that this has 2 components. There is a component, the rank of A is at most 1, and B times A is 0. And another component when the rank of B is at most 1, and B times A is 0. Probably have to put, here is A and here is B, I guess, right? The codimensions of these components are 4 and 4. So the red numbers are codimensions. Now I want to consider, say, 2, 2, and 3. Then I'm only going to give you the codimensions of the components. There are 3 components, and the codimensions are 4, 4, and 6. I'm going to give you another example. 5, 5, 6, 6, 6, 6. So again, is it clear what I'm talking about? There you have the ambient space, a vector space, the vector space of 5 by 5 matrices plus the vector space of 6 by 5 matrices plus the vector space of 6 by 6 matrices, and so on. And in that linear space, I consider the variety when this total composition is 0. Right? And the fact is that it has 5 components. Oh, okay. So it has a number of components is have codimension 19, 5 of them, and many larger than 19 codimensional components. Okay, so why this is relevant for your undergraduate students? Because if we really want to ask what is the reason for product of matrices of these sizes is 0, let's say that there are many reasons. There are okay, 5 plus many reasons. There are 5 plus many different cases why this is happening, but actually 5 of them are the main reasons. Because the point of view of 19 codimensional geometry, something that has larger codimension is measure 0. So there are 5 main reasons for the product of matrices of these sizes being 0. So what we will be interested in is just the codimension of this variety and how many maximal dimensional components there are. Okay, so let me introduce now some definitions. So D be a dimension vector. D0, D1, Dn. And then you consider the so-called representation, Creamer representation space, type A equioriented dimension D, which is just the you understand, so linear homomorphism from C or R, I'm going to write C now, D0 to D1, etc. from C dn minus 1 to C dn. Okay, and then in this representation space, I consider sigma dr. This is those tuples. Say A1 comes from the first one, An minus 1, or An comes from the last one. So those tuples, A1 to An, such that the full composition has rank at most R. When R is 0, then rank at most R means that the full composition is 0. So my examples where the composition is 0. Okay. And then the two important objects is lambda will be the codimension. I should decorate it with D and R, that I will not do. The codimension of sigma RD. So that means that the codimension of the largest dimensional components. And theta is the number of maximal dimensional components.
Okay, but you already switching to complex coefficients.
It turns out that
The real problem, the codimension would be still the same. The number could change if you go to the real problem.
Luckily in equioriented type A is the same, even the number. There is a good point about going real and complex where, in this part, in the singularity theory part, but in this geometric problem that doesn't play.
Lambda is not the same as the previous one.
It is the same.
It is the same.
It is the same. So lambda in the part that I erased is a real low canonical threshold, but for a particular model of machine learning machines, it is the number of maximal dimensional components of this variety. And okay, I will not there, but I told you the error estimate of the so-called Bayesian generalization error. But there's another one, this free energy or relative entropy, and that the first two terms, the first term is dominated by lambda, and the second term is dominated by theta, and then lower order terms. So even this theta plays a role in Bayesian learning theory. Actually, once we are here, and not everybody was very positive when I talked about neural networks. Maybe I tell you why this resembles at least neural networks. So what is a neural network? Neural network. Mathematically, it's a special type of function. It's a function where you apply a linear map, let's call it A1, and then compose it with the so-called activation map. Then you compose it with another linear map, and you compose it with the activation map, and so on. You can choose where to end, for example, let's end with the activation map. So so the capital A's, they mean linear maps. and the activation map is just x if x is even 0 if x is negative, and you do it component-wise. Okay, so imagine that you have you take a picture from the internet, and that's a vector, and you apply it to a linear map, then you get another vector. Now activated, that means that all the negative components you just change to 0. And then you apply another linear map, you get another vector, some of the components will be negative, change them to 0, and so on. The number of times you go through is called the number of layers of this neural network. Deep learning is when this is very deep, right? And then the composition is a special type of map. So the map depends on what the entries of these linear matrices, of these matrices are. That's what we will call the program. Okay. Right. So how does this work in the general? Maybe this last linear map will be such that the target will be one-dimensional, and then what the neural network is a map from, I don't know, from R2000, which describes a 2000 pixel photo. It goes to R, and maybe you want a function which solves the most important, like burningly important problem of the 21st century: how many cats are in a picture, right? And then you want to find the right entries of these A's, for which this function more or less tells you how many cats are in a picture. So the standard approach of machine learning is that you start with some random entries of these matrices, and then in the space of matrices, which is, as you can see, is this representation space, you run some gradient flow. But how do you know that function? What is this optimization function? How do you want? Which direction you want to go in the space of programs, or spatial neural networks, where you hire lots of undergraduates who will tell you how many cats are in a picture, and then you go to a certain direction, and then you punish or reward the program according to if it improved or not improved according to what the humans did. So that's the standard approach, the gradient flow. But singular learning theory is a different approach, and then we will meet that later. All right. So I wanted to talk about this so that you see that this is not very far from neural network, except I'm choosing the activation functions to be the identity function. Now you can say that this is totally wrong, because in real life this is a very important point of neural networks, that the activation function is not the identity function. But for that, I don't know how to calculate the low-canonical threshold. Now this is still used in machine learning as a toy example, and for this toy example, we can say something. Okay, maybe the last remark about neural network again is that why is this called a neural network, right? So, has everybody met this before, or should I talk about it a little bit? Okay. So when you
I have one comment maybe. So because you choose your activation function 1 to have the simplest problem, you are still in the language of complex or real algebraic sense.
Indeed, yes.
As soon as you would take such an activation function which inequalities, you go to semi-algebraic.
Exactly. Yeah.
And then estimating or getting the number of components is a much more difficult problem.
Absolutely. Yes. So this lambda, which they call the learning coefficient, is just not known. I mean, they make experiments and then they tell you what they should be, but for the right activation. Because by the way, you go to PD people's talk and they use different activation functions as well. But the problem is that it should not be algebraic. It should be absolute value of things like that.
So are we supposed to apply this to vectors with positive entries or something? Because it is a little bit weird for me. This activation depends on greater than or equal to 0.
I just don't see the point. So I think the actual form of the activation is not very important, because if you change it a little bit, then maybe you change it.
Yeah, what I was thinking is like these are linear maps, right?
Correct.
So I need to take more or less half of the vectors and forget about them, or turn them half of the things and turn
Half
them
of the
into
components,
0.
you mean?
Right?
Yeah. I think you probably all have this feeling that this function, the zero set of such function, a neural network, is some kind of piecewise linear hypersurface. I don't know how to draw a 200-dimensional piecewise linear. Okay, so that cuts the input. Say the input goes from Rn, that tells this Rn dimensional space to something. So the zero set is a piecewise linear function, and the belief is, and then if you use ChatGPT, which is very effective, that piecewise linear functions of this form, they can tell you if on a picture there is a person who is there's a shark in the picture or there is no shark in the picture.
Yeah, but that's
Somehow.
important. You can point to simulate two answers, yes or no.
Right. And then piecewise linear approximation, and this is a piecewise linear approximation. You just have to find which piecewise linear approximation. Okay. Where was I? Oh yeah. So why is it called neural network? Because if you go to your high school biology book, then there are pictures like this. There's a neuron here, and what it does is that it gets some kind of input from here and here and here, and then, which is some electrical signal. I don't know what it is. It does something to it. Maybe it adds them together. Maybe something like that. And if after it added together those numbers, if it's larger than 2, then it shoots out an input there. And if it is not, it doesn't reach that 2, then it doesn't shoot out that signal. And now you see that's exactly what we are doing. So there are lots of neural networks. They are sort of the components of these linear maps. And then you apply the linear function. So maybe at each neural, it adds them together. Maybe it adds them together with some weights. And if it reaches a particular number, then it shoots out an electrical signal. Okay, so that's why it is called neural network.
But the matrices capital A are linear. They are not affine. They are not affine transformations.
Actually, that's also a version. And different versions have different names and different conferences.
No.
You can make this affine as well.
No, what I mean is that all these neurons are equally sensitive. Like half of the time you get negative, half of the time you get positive.
Right.
And that is a little bit weird to me. If they were
But then after that you turn them away and then. Right. Okay. Something I forgot to point out, and I actually just erased it, is that when I did this 3, 2, 3, and the component codimensions were 4 and 4, and when I did 2, 3, 3, and the component codimensions were these. So let's keep that in mind. That what happens if you permute the dimensions? What is the dimension of the representation space for this one? It is 3 times 2 plus 2 times 3, which is, nobody knows that, 12. It's a 12-dimensional linear space, and in that there are 2 4-dimensional components. And this is a 9 plus 6, it's a 15-dimensional space, and in that there are 2 4. So the number of components changes. Okay, so keep that in mind. That we live in different dimensional spaces, and we shouldn't expect any relation between those. That's all. Okay, I think I'm finished with one slide. All right, so we will give 3 answers to the problem of what is lambda, what is theta. Answer 1 is probably the most interesting for us. For that, let's consider this so-called Pochhammer symbol, or inverse of it. This is a definition that for every non-negative integer, consider this rational function. And the way I want us to think about it, is imagine this is, you take it's a formal power series where q is very small. So 1 over 1 minus q is 1 plus q squared and so on. This probably has a name. This is probably the dilogarithm function. And I'm going to, or quantum dilogarithm. For a vector, this is just going to be And this is the definition that I multiply the PVIs for components. So the theorem is the following, that if you consider this power series, I'll discuss it. And this starts with eta times q to the lambda plus higher order terms. Okay, so let's digest this. So somebody gives you that dimension vector. Vectors are underlined by D. So you're given the dimension vector. Then you write down several power series. The first one for s equals 0. So what you do is take p sub s, which is just 1. But oh yeah, what does it mean that from a vector I subtract a number? I'm not going to write that. It means that I'm subtracting this number from each component. Okay. So that times the 1, 1, 1, 1 vector. So you okay. Let's consider r equals 0. Okay. So I want the product of the matrices to be the 0 matrix. So this is not even here, and this is not even here. So for s equals 0, you consider p sub s and p of d. And that will be your first formal power series. The next one, you plug in s equals 1, the p times 1, and then from each component of d, you subtract 1, and then you multiply those p's. But then you take it with a negative sign. So for the s equals 0, when it's a power series, it starts with 1. S equals 1, it's also a power series starting with 1. And then because of this s choose 2, s equals 2, it starts at, I don't know, at q squared, and then that's a power series. The next one is x, can you remember the binomial coefficients. The next one starts at q to the 6th, and then the power series. And you add them together with alternating signs. So the claim is that it is alternating sign. The first very many monomials will vanish. So just this alternating signs will be 0 for very long. And the first time this cancellation doesn't happen is in the lambda power. So that's the meaning of the theorem. And the coefficient that survives in terms of that is theta.
And the other coefficient also positive or non-negative.
So that's true. Yes, we also know
So
that.
you have a combinatorial definition.
Well, these are the Poincare series. So higher Bethe numbers. So okay,
So then
I'll tell you more.
lambda
Lambda is the codimension of the higher
these
dimension.
are the numbers from before.
Yes.
Correct.
Okay,
Yes.
okay.
Yes. Lambda of D and R.
And the vector is the
Is this dimension vector?
dimensions of the vector spaces, right?
Correct. This is, by the way, a super fast way of calculating these numbers. So even when I have this, then I could check the machine learning experiments and it just matched. But let me give examples. So let's just give a name to this. This is QDR. Okay. So Q0333 is equal to this. Q044. So what I mean is that imagine 6 copies of 5 is in here, 5, okay, and 3 copies of 6. And this is 28 times q to the 12th and 508 times q to the 13th and so on. So and these are milliseconds for a computer. This is just not an issue for a computer. So what does this mean? That if you have these dimension vectors, you go from 4 dimension to 4, 4 to 5, 5 to 5, 5 to 5, and so on. Then this the sigma has 28 maximal dimensional components, and the codimension of those maximal dimensional components is 12. So there are 28 different reasons for matrices of this size to multiply. So there are 28 main reasons why the dimensions of those matrices multiply to 0.
So I'm confused. One thing I missed the PD minus R minus SD is a tuple.
Is a vector indeed,
Yeah.
and this is a number. And what I mean by this is that you subtract this number from each component.
Okay.
Yes, yeah, I should be. Okay, so this is the 1, 1, 1, 1, 1.
This would be a Poincare series.
Yes. Poincare series. So equivariant. So this is no, equivariant Poincare series. So take equivariant cohomology.
And if D becomes negative, then
No, these are all non-negative. Okay, so I'll tell you a minute. So what happens is that you take that representation space. That representation has an action of the GS, right? And there's of course it's very easy to calculate its equivariant cohomology. First of all, it's a vector space. So GID equivariant cohomology of a vector space is just GID equivariant cohomology of a point. So I know what it is. On the other hand, I can forget what it is and just think of it that representation is cut into orbits. And I want to calculate the Poincare series of each of the orbits and want to add them together. And because of this is a spectral sequence that I start to do here. So if there's an orbit, or say a component, and we have a contribution to the spectral sequence, this is a spectral sequence that converges to that. And the contribution of one orbit is put in a particular column, where this column is the codimension of that orbit. Okay. And what has to be there, that's also not very difficult. Like we can maybe discuss it in the discussion if you want. Maybe graded character is another word. Anyway, so you see the point that this spectral sequence, by the way, degenerates because everything is complex. So only the even components are here. So it is by definition degenerate. And then the sum of the ranks, or if you do it over the field, then sum of the dimensions in diagonals have to add up to the given degree components of that. And now, if you do it for all of the orbits, then you get the so-called quantum binomial pentagon identity. But now I want to cut out those orbits for which the product is non-zero. If I cut out those orbits, then I get this. It's not totally trivial, so maybe, again, I wasn't intending to give a proof, but I tell you some statements, what goes into the proof. So proof ingredients. There's a spectral sequence to that. Plus, a very important Quiver algebra that I want to come back to, that the indecomposable, okay, it's just for those who understand Quiver language, the longest root indecomposable is both injective module and projective module. And the third component is there are four components. There's the normal size to an orbit in Quiver world can be written as X. And then the fourth component is a beautiful identity of Euler, which I probably lost. Oh yeah, here it is. Okay. Some Euler identities that if you want the power series of Pochhammer symbols, or you want the power series of negative 1 to the s, q to the s, choose to Pochhammer symbols, and these are inverses of each other. This is a famous beautiful result of an officer in the Russian Navy, Leonard Euler. So one side is the so-called infinite Pochhammer symbol, and the other is 1 over the infinite Pochhammer symbol. And so you probably see that this is called the quantum bilogarithm. Quantum bilogarithm has to come up. So that's why it's very interesting. Donald's and Thomas type of quadratic form in the exponent appears. Okay, so I really I'm not planning to say too much about the proof, but this is what you have to put together. However, when I came to this answer, I was shocked, and I spent considerable amount of time and energy to find a mistake in my proof. Well, this is the statement. Because this answer has a feature which is very counterintuitive. The formula that we gave for lambda and theta doesn't depend on the permutation of the components of D. Right? You see, nothing on the left-hand side depends on the permutation of the components, essentially because of this definition. It doesn't matter how you. So that a corollary is that lambda and theta are independent or permuting, or unchanged under permuting the components. And I just found that this cannot be, right? If you multiply matrices 5, 5, 6, 8, or 8, 5, 6, 5, it's a completely different problem. We are living in a different dimension of vector space. And I also learned from Macaulay and Singular that there are different number of components, so it just cannot be right. But it is right. This is a theorem. There are different number of components, but the same number of maximal dimensional components. Quite amazing. Finding all the components seems to be a very, very difficult problem. That problem is on the nature of primary decomposition. But it turns out that finding the maximal dimensional components is a cohomology level problem, which is not as difficult as primary decomposition. So this is true. Right. And then some time ago, there was an example on the board. I think it was 2, 3, 3. I permuted them in 2 different ways. And there were, for one of them, components were 4, 4, and the other one was 4, 4, and 6. You see the number of components changes. The number of maximal dimensional components didn't change, and the dimension of the codimension of the maximal dimensional component didn't change. So it's a big surprise, and that it's a miracle and a luck that this can be solved without very deep commutative algebra.
And you don't have a simple explanation for that?
No, except there will be an answer 2 and an answer 3. An answer 3 will be an explicit formula. You give me these, and I tell you what the number is. And now with Jakub we have a bijection. So for that number we will produce the components. But I don't know if it's an explanation. It's an explanation because this falls out of the proof that these are the ones. Okay. Maybe I didn't give you any description of these components. These components are very massive in the sense that, maybe last example. This was an example before. And I told you that there are 5 components of codimension 19. One of the components is this. That A1 has rank 3. I'm not writing rank. This means that the rank is A3. The rank of A2 is 4. The rank of A4 is 4. The rank of A2, A1 is 2. The rank of A4, A3, A2 is 2. And A4, A3, A2, A1 is 0. So this is the description of one of the 5 19 codimensional components. So now if I permute these numbers, then there will be another 5 19 codimensional components, but you will not, it's not obvious at all how to write those ones out of these ones. Of course, there's a trick that I might come to later. Okay, can we go over and can we go further? And then I'm going to give you answer 2 to the same problem. Because I was of course very happy with answer 1, but so the nature of the problem, nature of the formula is just not good for asymptotic understanding. If somebody tells you that my D is such that there are 100 levels and each of them is 200. I don't know that in this alternating sum, what will be the first exponent where the cancellation doesn't happen. Just no idea. So that's why we push it further. We want asymptotic understanding to compare it with machine learning story. For example, with this story that overparameterization will not hurt us. Okay, so answer 2 is the following, that suppose D is, of course, D0, D1, Dn. The first thing I want is rearrange them in increasing order. To follow traditions of algebra, first I wanted to them decreasing, to call it a partition, but it's just more convenient. So it is the same multiset, but order them increasingly. I'm going to write down a quadratic integer program, which is the following. I want to minimize or maximize, I can't remember, maybe maximize EI times EJ plus DJ minus 1. Subject to the condition that sum of the EIs from 1 to n is D0 prime, and each of them is a non-negative integer. All right, so let's see. Let's digest this. I haven't said the theorem yet. Or maybe I said the theorem and then we digest. The statement is that the solution of this quadratic integer program is lambda, and the number of times this optimum is taken is theta. Okay, so digest this. So what kind of quadratic integer program do we see here? So the EIs are the variables, okay? The variables is E1, E2, En. And what do I know about them is that each of them is a non-negative integer, and they add up to a given number. This given number is the smallest of the dimensions. So the geometry would be something like this in the right dimension, that you take the integer points of this, what I just learned the other day, that you call it probability simplex or something. Okay, whatever. See the integer points of this complex, and on that one you cook up a quadratic equation. Okay, these D's are again amazing that these are certain differences between your components, but they're random. Maybe the D2 minus D7 or something like that. So you only see which one to subtract from each other when you order them increasingly. So that's why you shift. And then this is just a quadratic function. And the question is, for which of these points is this quadratic function the largest? You find the largest number, and that is lambda. And maybe the story is that it's largest for these three things together, and then theta is 3. So that is the second one. Okay, so the proof ingredients is queer, essentially the Lehalleur theorem. So Lehalleuer's theorem is rediscovered by data scientists under the name of topological data analysis. Lehalleuer's theorem for pure algebra. Plus this story about that the normal size to an orbit is the x of the associated indecomposable with itself. So these are the ingredients. You see, if I have a good algebraic way of thinking about the normal size to an orbit, and I know this is an algebraic way, and then I know that x is bilinear, so eventually this boils down to a quadratic formula, and that's what it is. Just have to set out that right. Interestingly, the proof of answer 2, I forgot to say, the proof of answer 2 is actually much easier than the proof of answer 1. And it's probably a better formula, except I can only prove it if I know that the answer is invariant under the permutations. So all that big machinery of homology and everything is needed for the corollary. If you give me a conceptual reason for the corollary, that one is not needed. By the way, I have another proof of that corollary that uses characteristic classes of singularities. But I will certainly not have time for that. That's more complicated than what I put the answer on. And then it's time to go to answer 3. Answer 3 to the same problem is that for that I need a definition that is almost in the machine learning literature, except incorrectly, but this is correct. So this is a number between 1 and n. Now for that number, lambda is equal to m over 2 times sum of di prime over m fractional part times 1 minus the same fractional part. So this is the same thing. Minus m times m minus 1 over 2 times the sum of the di primes over m squared. Oh, plus sum of di prime dj prime. Okay, of course, you don't learn too much about this, and I might have made some small mistake, but probably not. But this is a totally obvious formula, like high school level formula. This denotes integer part. There is some number theoretic story in the background, and that comes from the fact that this quadratic integer program is very similar to minimizing at distance. You see, this is not a distance function, but it's not very far from ei squared plus ej squared and so on. So by some algebraic tricks, you bring this to a distance problem, and then you want to minimize a distance from a given point to the integer points of this simplex. And so how difficult that is. Somebody gives you the integer points of a simplex and then a faraway point. The problem is that the plane or hyperplane of this simplex is important. And if you project your point there, then maybe it's outside of the simplex. Then in certain coordinates, this is not important. So first you have to understand which phase and which dimensional phase you need to project. And that's what this m is. But once you understood which dimensional phase you want to project, then your problem is finding the closest point in a type A lattice to a given point. So, and that is solving convex geometry called the Voronoi cell, that if you have a lattice, then there is a Voronoi cell around each point, and that is not very difficult. You can either you look it up or you solve it yourself. For type A lattice, the Voronoi cells are very simple, and then this comes out. So that's the proof of answer 3. But now you have answer 3, then you have a beautiful consequences. Oh, it's just this. Integer points, so this one is I think dimension 2, that would be the
This you still need to know that it's independent.
yes, yes. The answer 3, I do it from answer 2, and answer 2 depended on the fact that it's independent of the permutation. And again, I'm not putting answer 4, so we have now bijection between. I have a list of like we can describe what the components are, and there are this many. What is written here? I'm not writing down the formula for data; it's something similar. So maybe just a corollary, which now is the machine learning way of thinking about that. But suppose that your so-called hidden variables are all are the same, and you have an n-layered, or as usual, we want it n+1. Okay, it's an n+1 layered linear neural network, and the number of hidden variables at each stage is d. Okay, then you just want to understand this formula, and then it will tell you that lambda is approximately because this frictional part and integer part makes it a little bit off, but it is it's just a high school consequence of that. So what does it mean? And this is what matches the training coefficient experiments, is that it doesn't depend on n, or just it depends on n very mildly. So if you increase the depth of a linear network, it doesn't hurt your generalization. Actually, it's in the denominator, so actually it halves your generalization. It's quite amazing. So of course, the number of hidden variables, the width of your neural network, it matters, right? If you have to work with 1,000 by 1,000 matrices or million by million matrices, the million by million matrices will be more difficult. Okay? That you cannot get rid of, and it has to be d squared in some sense. But people were worried that if you go deep learning, you increase the number of layers of your neural network, then you won't be able to train it. And no, you can train it, and this is this is really nothing. Okay, Paolo, I think I have 3 minutes left.
I think you have more. Relaxed.
That's certainly true. But
Can I ask? You're calculating a number lambda, which comes from matrix multiplication. What's the relation?
Yeah,
that means that this is a pro-canonical threshold or something.
Yes. So that's what I want to say. Probably after in the disguise of interrogation, or what it is called discussion, and maybe after a little break. But I'm happy to talk about the singular learning theory story, and with my partial understanding, but there will be some feeling of that the real pro-canonical threshold of something boils down to this number, how many maximal dimensional components of this variety has. Okay, so may I suggest to have a break, and then people who want to return will discuss the singular learning theory.
Okay, so that's